Hello, my name is Samuel Chiang Housing, and today I'm gonna present about the regulator DC power supply employing IC voltage regulator with an adjustable DC voltage output. First of all, voltage regulator is a component that produces fixed output voltage of preset magnitude that will remain constant even though the input voltage or load condition changes. Typically, a basic power regulator will consist of transformer, rectifier, filter, IC, regulator, and load. Each of the component is essential to make sure that the circuit works properly. As we can see in the figure in the slideshow, that is the component required in a voltage regulator. For the history of voltage regulator, it's developed in 1967 by Sir Robert Junior Whitler. He designed the LM109 and also released the integrated power regulator design of LM723. As we can in the slideshow, it is shown the schematic diagram of LM109. The applications of voltage regulator is very wide. Among it is the usage of voltage regulator in the microcontroller, LTC3255, an example. 7805 power regulator can be used to fix the output voltage at 5 volt for the microcontroller to run. Next is the usage in the automobile. In the typical alternator circuit, it's shown that the voltage regulator is required so that the voltage to the ignition switch and to the battery is stable. For the theoretical explanation, we use multi-sim simulation to simulate and measure the waveform at input AC voltage, step-down transformer, full-wave rectifier, filter capacitor, DC output voltage with maximum and minimum adjustable resistance. For the calculation, to calculate the input voltage, where the voltage is still in VRMS, so we have to convert it to Vpeak by using Vpeak equals to VRMS times by sub2. For the Vpeak after the step-down transformer, we use the Vpeak for the previous calculation, which is the Vpeak of the input voltage divided by 20, where we derive it from M1 over M2 equals to Vpeak of the input voltage over the Vpeak after the step-down transformer. M1 N2 is the number of turn, the primary coil for the N1 and the secondary coil for the N2. For the full wave rectifier, VDC equals to 2 over pi times by Vm, derived from formula of half wave rectifier, VDC equals to 0.318 Vm, where the full wave rectifier is the twice of half wave rectifier formula. That is why we get 2 over pi times by Vm. Then to convert the VDC to VRMS, we use VRMS equals to 0.308 times by Vm. For the filter capacitor, VR, the V ripple of the RMS equals to I over 2 FC, where I is the current, DC current measured after the IC regulator and the connection between R1 and R3, the connection there. Then for the filter capacitor, the formula was used to smooth the rectified ripple into a smooth ripple.
Next, we are going to explain how we going to carry out the experiment. First of all, we design our circuit by using the multi-sim software before assembling the hardware. This is to prevent any circuit failure such as IC voltage regulator and other components burns due to high voltage input from the power supply. This figure shows the circuit that we have designed by using the multi-sim software. We measure the waveform after step-down transformer, waveform of filter capacitor, waveform of DC output with minimum adjustable resistance, and the waveform of DC output maximum adjustable resistance. Next, we will show the result of our experiment. This simulation of circuits show how we measure the input waveform and waveform after the full wave rectifier by using the multi-sim software. The next part will show all the waveform and the calculation at each part of the circuit. By using multi-sim, we have measured the waveform of input AC voltage, waveform after step-down transformer and its peak voltage, and the waveform after full wave rectifier. Next, this simulation of circuit will show how we measure the waveform of filter capacitor and waveform of DC output voltage. So these are our results of our hardware by using an oscilloscope. We also verify our result by using a multimeter to compare the result we got from oscilloscope. So after we obtain our result by using different kind of methods, we arrange the results in a table for comparison, and this table shows the result of simulation, theoretical and practical value. And if we compare all three kind of methods, the value we obtain is almost similar. But there is also some slightly different between the multimeter result and the multisim due to the less efficiency provided by the step-down transformer and also the loss of energy in the form of heat. And we have some limitations towards our hardware measurement. We found that we cannot measure some waveform and voltage current measurement directly on our hardware, which already soldered in the protoboard. And these waveforms are waveform after the full wave rectifier, waveform of the diode, and also the current at the connection between the 2.2k ohm resistor and the adjustable resistor. This is because the limitation of the protoboard after the hardware was soldered. Measurements should be done on the breadboard beforehand before soldering it on the protoboard. And a heatsink should be used to improve the efficiency of the circuit by allowing the heat to disperse from the IC regulator. So in conclusion, we already achieved our objective, which is to design and create a functioning IC voltage regulator with adjustable resistor. And this application is very important for students because it can prevent error and mistakes such as components burn due to high voltage as the experience gained from the experiment. The application of multi-sim is also important because it can allow the students to first design and test the circuit virtually before assembling it into a protoboard. This can minimize the number of mistakes that can occur while the circuit is connected to the power supply. All in all, this experiment allows students to realize how much of the usage of IC regulator circuit is being integrated into our daily life and for the industries. Alright, our sharing is already comes to the end. Thank you very much.